I'm Phil Lundrigan from Brigham Young University. I'll be talking about on-off noise power communication. But before I get to that, I want to give some context of how this research came to be. I'm part of an NIH grant that looks at children with asthma. So we were tasked with building an air quality sensor, Wi-Fi air quality sensor to monitor the air quality in homes. And so we put these air quality sensors typically in 3 places within a home, usually living room, bedroom, and outside for a typical deployment. And it was a very interesting and informative experience having this Wi-Fi sensors in homes, actual homes, and collecting a lot of data about that. And one of the interesting side effects was that we weren't the ones actually deploying these sensors. Someone else was deploying them, and so they didn't always pick the right place to put them in. The study told us where we had to put the sensors, and so we had to kind of just adapt to where it fit, and it wasn't always ideal to where the best wireless signal would be. And so this presented a lot of interesting challenges that we weren't expecting initially within this. And so the big motivation for this research was this screen that I've spent hours looking at and scratching my head. This is a dashboard that we built just to monitor our air quality sensors. So you see, there's 3 different deployments with 3 sensors each. And we'd sit here and we'd say, well, why is monitor B016 disconnected? It's been disconnected for 5 hours. What's going on in that home that could be causing that? And what's interesting within a deployment where you have real participants doing this is that you can't just go call them anytime you want and check and say, hey, what's going on with my sensor? Or you can't go over their house anytime you want and knock on the door and unplug and plug it back in. And so we had to be really careful about when we asked our participants to do various things. And so we started to gain an intuition of kind of these different problems we encountered as we had our sensors deployed. And you can imagine a spectrum of kind of less severe problems to more severe. A less severe problem would be Wi-Fi is just not working. It's disconnected momentarily. That's not a big issue because our sensors are designed to handle that. And so they'll still collect data while they're offline, and then when they come back online, they'll reconnect and they'll upload the data. But on the other end, there's something like maybe a bug in the code, or there's a hardware malfunction, or probably the worst case would be no power. It's either purposefully or accidentally unplugged from power. That happens all the time in homes. And why the no power and these other ones are more severe is because we're losing data. In a study like this, epidemiological research study, having no data is the worst case scenario. That can invalidate days of worth of data if you don't have the right data at the right time. And so what we found is, seeing at the dashboard, we couldn't tell which one was which. Has the sensor been unplugged for the last 5 hours and won't be plugged in for the next week? Or is it just a Wi-Fi disconnect and it'll come back online at some point? So what we really wanted to be able to do is draw a line and say, you know what, this is a Wi-Fi disconnect. Even if there's nothing we can do about the Wi-Fi disconnect, just know it's a Wi-Fi disconnect, it will come online eventually and it'll be okay, versus no, this is a power outage. We need to bug the participant, we need to fix this now. We actually had a participant drop out because we were asking him early stages of our deployments, asking him too much. And so this is a real consideration. We don't want to bug our participants too much. So we really wanted to figure out a way to classify these 2 different types of problems. And what we found as we dug through the data is the cause of this would be these sensors were deployed on the edge of connectivity. Here we have a Wi-Fi sensor, in this case our air quality sensor, but it could be any Wi-Fi sensor, connected to an access point. And it's connected at the lowest data rate that this access point supports. In this case, it's 6 megabits per second. It's on the edge. Maybe it's outside or it's far away from the access point. So that anything that happens to the sensor, let's say like a laundry basket is put in front of the sensor, any little change in the environment can cause that sensor to go offline. Just enough of the attenuation of the signal can cause it to go offline. And now it's disconnected. What we found is that Wi-Fi, it limits the slowest data rate. So that's set by the access point, and if you can't achieve that data rate, you are no longer connected to the access point, and you can no longer upload data as a result. And so we started looking at alternatives because it was such a big problem. So, well, what if we went with cellular or LoRa or even an upcoming protocol, Halo, and see if we could do something about that? And all these have some severe drawbacks, in terms of cost, or we have to end up deploying our own gateways in terms of LoRa, or wait for a new technology to come about. And none of these fit our needs very well. And we already had deployments out in the field. It'd be hard to switch those out, and it costs money and add complexity to our system. So we really wanted to stick with Wi-Fi. So we asked ourselves, could we build a communication protocol on top of Wi-Fi that has a longer range than Wi-Fi? And so that's what on-off noise power communication is. And let me give you some general intuition about how it works. I call it ONPC for short, on-off noise power communication, ONPC. So here we have our context where we have our sensor that's disconnected because of a laundry basket or some other obstruction in the way our environment's changed. The intuition behind this is that the Wi-Fi sensor is disconnected. It's not associated with the access point anymore. But when it transmits out, some of the signal could still be received potentially by the access point. Not enough for it to decode the frame that client is sending out, but it can still have an effect on the signal and on the noise. So what if instead of worrying about frames, we looked at just the noise? We no longer try to decode frames, we just look at the noise instead. And so let me kind of give you an illustrative, what I mean by that is, maybe this client transmits in a certain pattern of on and offs. These can be any transmission whatsoever, so a short on, a long off, and then a long on. And on the receiving end, it doesn't try to determine what those on transmissions were, what the frames were, or the data was. It just looks at the noise and sees the effect that those transmissions had on the noise. They would be able to correlate this and set up a way of communicating. And so that's what ONPC is. It's a physical layer protocol on top of Wi-Fi. On the transmitter side, all it does is sends out beacon frames in a pseudo-random pattern. So Wi-Fi is all the hardware is still taking place. It's still modulating Wi-Fi however it needs to do, depending on the protocol we're using in the data rate. We're just transmitting on and off, just sending out beacon frames in a pseudo-random pattern. And on the receiving end, it's looking for that pattern in the noise. And the cool thing about this is it's implemented purely in software. We didn't have to make any changes to the hardware or to the firmware to make this possible. And it extends the range of Wi-Fi using spectrum techniques. And so we're trading off the lower data rate for longer range. Now the data rate is quite slow, 1 bit per second, which for this, the fact that we weren't able to communicate before, 1 bit per second is a huge improvement over no communication at all. And for our application, that works, because an IoT device, just telling you if it's online or offline, 1 bit per second is enough. Or to send out something that's not reading very often, 1 bit per second is enough for our application. So then the transmitter, so here's a flow chart of the transmitter in terms of we have some data we want to transmit out. We have some kind of symbol. In this case, it's a 4-chip symbol. They're a lot bigger than the actual implementation of this, but just for illustrative purposes. We correlate that together and come up with a pattern of ones and negative ones. We then convert this into on and offs of beacons, and we send out these beacons in this pattern. And on the receiving end, the access point is just constantly measuring the noise, and it's running this through a limiting filter, and then it correlates it with the symbol and looks for it. If there's a high correlation between the noise that's been collecting and the symbol, then it knows it's detected a bit, and so it's able to receive the data that way. We ran into a lot of different challenges to make this possible. A lot of these were issues because we want to implement this purely in software. And by implementing it purely in software, we're able to do an over-the-air update to now add new capabilities to our sensors that were not possible before. So we had issues with timing requirements. We didn't want to ignore carrier sensing. We're still carrier sensing compliant, so we had to deal with timing and how to deal with that, and the fact that this is all done in software, so when you tell it to transmit out a frame, it doesn't do it right away. It might wait a while. Or when you tell it to receive collect a noise measurement, it might take some time for that to happen. So there's a lot of challenges that we had to face along the way that I won't be able to address. But going back to the context of the air quality sensors, we wanted to build an application that could utilize ONPC's new capabilities. By extending the range, now a sensor that was on edge of connectivity now isn't on the edge of connectivity anymore. Now it can communicate because of ONPC's capabilities. So we designed an application to tell us if the sensor is still alive or not. We called it Staying Alive. And so how it works, Staying Alive, is that when it detects that it's no longer connected to Wi-Fi, when it's no longer connected to Wi-Fi, it starts transmitting on PC mode and sends out a keep alive message. And this allows a remote manager, like us in this case, looking at that dashboard to say, I know the sensor is disconnected, but I know it's still alive. Hasn't been powered off, and so I can just wait until it reconnects to Wi-Fi. So now the remote manager has more information at their disposal. So to evaluate ONPC, we first took it outside. We wanted to see how does this work without much interference. And so what I did is I placed an access point in the park. Here, you can see it in orange. And I walked as far as I could away from the access point until Wi-Fi stopped working. It was no longer associated with Wi-Fi anymore. And I stopped right there, and it went into ONPC mode, and I collected the data. So this is the relative distance. It's pretty far given the environment. And so in these 6 different locations, we had 85% symbol reception rate with only a 4% false positive rate. So it shows that Wi-Fi, we're able to go beyond what Wi-Fi is capable of sending. We wanted to take it one step further and see, well, how farther can we go than Wi-Fi? So we chose one location, in this case location 5, tried different places, and the results for location 5C, we were able to get 72% reception rate. And I should put this, but that was 62 meters farther than what that distance was. So we're able to go well beyond what Wi-Fi was capable of and still have a reasonable symbol reception rate and false positive rate. And I want to remind you that for our application for staying alive, 72 is plenty. As long as you get a couple of keep alive messages every minute or every hour, that's enough for a remote manager to know that the sensor is still alive and okay. Then we took our system to a home, a more kind of fitting application for these air quality sensors, and we placed our ONPC transmitter. Or first we put the access point was down in the basement on one corner of the house, and we found a dead spot in the home on the other corner on the 2nd story, and we ran our ONPC transmitter, and there was plenty of interference here. We had 5 neighborhood access points all on the same channel, and lots of other devices all talking on the home network, and we were on that channel as well. And we had a 51% symbol reception rate and a 0% false positive rate. So once again, it's not amazing, but it's perfect for our application. Being able to receive a couple of symbols every few minutes is plenty for staying alive. Next, we wanted to experiment with how many different transmitters can we support. And so we did up to 5 transmitters, and this is made possible because the symbols that each ONPC transmitter is transmitting out is an orthogonal code to each other. So they're able to still communicate and decipher which one is transmitting, and we were able to support 5 devices. And then last, we wanted to look at what's ONPC's effect on Wi-Fi, make sure it doesn't negatively affect it. And so we did a couple experiments here where we first put we had a laptop that was using iPerf, sending UDP packets at different rates, unlimited being as fast as possible, and then 5 megabits per second and 1 megabit per second. And we did in 2 different scenarios. One where the client was very close, the laptop was very close to the access point, and the ONPC transmitter was far away. And then another case where the Wi-Fi client was far from the access point. And the only time that ONPC had a negative effect on the Wi-Fi was when the Wi-Fi client was up close to the access point and was sending unlimited data. As fast as it could send the data, it was sending it. And we don't feel like that's a very representative scenario. We wanted to see what the bounds were, but this is not a typical home environment to send unlimited data for as quickly, as long as possible. It's much more 5 megabits or bursty traffic, and so ONPC has a very little effect on the home traffic. So in conclusion, ONPC allows Wi-Fi devices to transmit over longer ranges than standard Wi-Fi, done purely in software. There's no hardware changes required. This opens up a lot of different possibilities, one of them being that we were able to create this application for IoT managers to then monitor these sensors. What's a really exciting thing about this is that nothing I said here is specific to Wi-Fi. All we need is the ability to receive noise measurements and transmit out at certain times. And so we're excited to try out different wireless protocols as well and see how well that works. That's it. Thank you.